Good day, everyone, especially to you, Ma'am Ivy. We are here to present a report about gears and cams.
But before that, let me introduce to you my group members. This is Paulo, this is Janeline, this is Janice, and I am Teresa, and we are
The Group 4.
So the overview of this entire report is about gears, pulleys and belts, chains and sprockets, cams, linkages, and other devices are commonly used to transmit power and motion from one machine member to another. Gears are one of the most common drive transfer mechanisms. Gears can change rotation direction, rotation speed, and axis orientation. Cams can change rotational motion into reciprocating motion. Both gears and cams are commonly used in automobile engines and transmission. Understanding gears. Gears are used to transmit power and rotating or reciprocating motion from one machine part to another. They may be classified according to the position of the shafts that they connect. Parallel shafts, for example, may be connected by spur gears, helical gears, or herringbone gears. Intersecting shafts may be connected by bevel gears, having either straight, skew, or spiral teeth. Non-parallel and non-intersecting shafts may be connected by helical gears, hypoid gears, or a worm gear. A spur gear meshed with a rack will convert rotary motion or reciprocating motion. Using gears to transmit power. The friction wheels transmit motion and power from one shaft to another parallel shaft. However, friction wheels are subject to slipping and a great deal of pressure is required between them to create a necessary friction force. Therefore, they are usually used for low power applications such as CD-ROM drives. So this is the example of friction gear. And spur gears have teeth on the cylindrical surfaces that fit together and transmit the same motion and power without slipping and with reduced bearing pressures. So this is the example of spur gears. To make gears operate smoothly with a minimum of noise and vibration, the curved surface of the tooth profile uses a definite geometric form. The most common form in use today is the involute. So this is the involute gear. Constructing a base circle. The involute tooth form depends on the pressure angle, which was ordinarily 14.5 degree and is now typically 20 or 25 degree. This pressure angle determines the size of the base circle. From this, the involute curve is generated. So this one, the base angle and the tooth of the gear. The involute tooth shape. If the exact shape of the tooth is desired, the portion of the profile from the base circle to the addendum circle outside diameter can be drawn as the involute of the base circle. So this is the addendum in the gear. Ang kibali ang ang isa ka tooth sa gear ang katunga ana, ang upper half sa isa ka tooth sa gear is the addendum. Ano siya?
Spacing gear teeth. Suppose that number of teeth equals 20 and diametral pitch equals 4 for a 14.5 involute tooth. The number of spaces should be 2n, twice the number of teeth, to make the space between teeth equal to the tooth thickness at the perfect circle. Rack teeth. Gear teeth formed on a flat surface are called a rack. In the involute system, the sides of rack teeth are straight and are inclined at angle equal to the pressure angle. Working drawings of spur gears. A typical working drawing of a spur gear, because the teeth are cut to standard shape, it is not necessary to show individual teeth on the drawing. The drawing actually shows only a gear blank, a gear complete except for teeth. Spur gear design. Spur gear design normally begins with selecting pitch diameters to suit the required speed ratio, center distance, and space limitations. The size of the teeth depends on the gear speeds, gear materials, horsepower to be transmitted, and the selected tooth form. Worm gears. Worm gears are used to transmit power between non-intersecting shafts that are right angles to each other. A worm is a screw with a thread shaped like a rock tooth.
Working drawings of worm gears. In an assembly drawing, usually the gear teeth are omitted and the gear blank represented conventionally in the lower half of the circular view. On detailed drawings, the worm and gear are usually drawn separately. Although their dimensioning depends on the production method, it is standard practice to dimension the blanks on the views and give the cutting data in a table. Note: dimensions that closely affect the engagement of the gear and worm have been given as three-place decimal or limit dimensions. Other dimensions, such as rim radius, face lengths, and gear outside diameter, have been rounded to convenient two-place decimal values. So these are the examples of working drawing of a worm gears. So what is a worm gear? A worm gear is a gear consisting of a shaft with a spiral thread that engages with the drives a tooth wheel. Worm gears are an old style of gear and a version of one of the 6 simple machines. Basically, a worm gear is a screw butted up against what looks like a standard spur gear and slightly angled and curved teeth. So how worm gears work? An electric motor or engine applies rotational power via to the worm. The worm rotates against the wheel and the screw face pushes on the teeth of the wheel. The wheel is pushed against the load. Bevel gears. Bevel gears are used to transmit power between shafts whose axes intersect. The analogous friction drive would consist of a pair of cones with a common apex at the point where their axes intersect. The axes may intersect at any angle, but right angles are most common. So these are the examples of bevel gears and friction cones. Bevel gear definitions and formulas. Because the design of bevel gears is very similar to that of spur gears, many spur gears terms are applied with a slight modification to bevel gears. The pitch cone is shown as the triangle AOB and the pitch angle is half of angle AOB. The root and the face angle lines do not actually converge at point O but are often drawn as if they do for simplicity. So these are the example of bevel gear terminology and the formula. Working drawings of bevel gears. Like those for spur gears, working drawings of bevel gears give only the dimensions of the gear blank. Data necessary for cutting the teeth are given in a note or table. On detailed drawings, each gear is usually drawn separately and fully dimensioned. Placement of the gear blank dimensions depends largely on the manufacturing methods used in producing the gear, but the scheme shown is commonly followed. A single sectional view will usually provide all necessary information. If a second view is required, only the gear blank is drawn, and the tooth profiles are omitted. Two gears are shown in their operating relationship. So, the working drawing of bevel gears. So, what is bevel gear? A bevel gear is a tooth rotating machine element used to transfer mechanical energy or shaft power between shafts that are intersecting, either perpendicular or at an angle. This results in a change in the axis of rotation of the shaft power. Aside from this function, bevel gears can also increase or decrease torque while producing the opposite effect on the angular speed. Stock gear models and drawings. A great website where you can find stock models for gears is the Stock Drive Products / Sterling Instruments site at sdp-si.com. When gears are ordered to use as standard parts in an assembly, a detailed gear drawing is not necessary. A table showing the gear information is often sufficient. A stock drive product, Sterling Instruments, provides downloadable CAD models for the parts they sell. B. Several CAD formats are available for download. C. An interactive viewer allows you to view and rotate the 3D model via the web. Cams. Cams can produce unusual and irregular motions that would be difficult to produce otherwise. A shaft rotating at uniform speed carries an irregularly shaped disc called a cam. A reciprocating member, called the cam follower, presses a small roller against the curved surface of the cam. Most CAD software provides tools to generate cams from design data, so you will not typically draw them manually. A. Basic cam principle. B. Automobile valve cam with flat face follower. C. This cam with roller follower attached to the linkage. Pellet steel cam for Ford 4.6/5.4L V8. Camshafts.
Displacement diagrams. The motion of the follower is our first concern. Its rate of speed and its various positions should be carefully planned in the displacement diagram before the cam profile is constructed. A displacement diagram is a curve showing the displacement of the follower's ordinates on a baseline that represents one revolution of the cam. You can use any convenient line to represent the 360 of the cam rotation. Cam profiles. The disc cam rotating counterclockwise on its shaft raises and lowers the roller follower, which is constrained to move along the straight line EV. The displacement diagram at the bottom of the figure shows the desired follower motion. Therefore, the base circle is divided into 12 divisions corresponding to the division used in the displacement diagram. These divisions begin at 0 and are numbered in the direction opposite the cam rotation. So, mao ni siya guys, ang kuan kay nasa kilid, kani na circle, mao ning displacement diagram, o kaning nasa ubos, mao ning cam profile. Offset and pivot cam followers. If the follower is offset, an offset circle is drawn with center O and radius equal to the amount of offset. As the cam turns, the extended center line of the follower will always be tangent to this offset circle. If the roller is on a pivot arm, then the displacement of the roller centers along the circular arc AB. The height of the displacement diagram should be made equal to the rectified length of arc AB. The initial point of contact is at A, and points 1, 2, 3 represent consecutive position of the follower face. So, mo ni ang pivoted and flat face followers kang nas ubos. Then, the second one is cylindrical cam. O kaning third, mo ni kagaina. O kaning this cam profile with offset. Cylindrical cams. A cylindrical cams of diameter d is required to lift the follower rod a distance EB with harmonic motion and 180 degree of cam motion, and to return the rod in the remaining 180 degree with the same motion. The pitch curve is drawn to represent the required motion, and a series of roller circles is drawn to establish the sides of the group tangent to the circles. To complete the front view, points on the curves are projected horizontally from the development. Other devices. When the distance between drive and drive-in shafts make the use of gears impractical, devices such as belt and pulley or chain and sprockets drives are often employed. Layout and detailing standards vary somewhat from one company to another, but design procedures and specification method may be obtained from almost any good textbook or handbook or mechanical design. Gears using Autodesk Inventor Design Accelerator. The Autodesk Inventor software Spark Gear Component Generator Design tab, which you can use to enter the defining details for the gear pair. Clicking the Preview option shows the value on a pictorial representation of the dimensional features for the gear. Gear drawing specified information needed to manufacture the gear using table. The gear table that can be automatically generated using the software. Design tab of Autodesk Inventor Spark Gear Component Generator. Preview showing values and a representation of dimensional features. 3D gear model. Table of information needed to manufacture the spark gear. And the last one, assembly drawing for Weaver Lip Tanner.
Wala, dito ra sa una. Ay, usakto din, no? So, magtuplog pa ka, mag-next.
tuplok pa
Ay,
ka
ikaw-
next pagka mag-
Ay, pag mayon ako, we will be...
Hamang, next
Discussing.
na. Na.
We're here to
Discussing na.
we're here to present.
Ay, ako na lang
you
grabe,
or
ikaw
to-
dali kay ikaw may kon mag.
Ay,
Sige, bila lang.
Ay, sige, ikaw istorya kay dire man ang
Ayaw.
istorya.
Diya pud.
Nagbailawan ta ikaw.
Sige, next.
Ako na action, kibali na yung amang.
Interpreter.
Oh.
Ang gulo yun.
Balik magapon ako ng buhok mo.
Eh, malun.
Nga anak ka para di maklaro ang dili.
Iskot mo na magnamatyan.
Ay, sa stop na niya i-flip